Hello and welcome to Math Zone African Motives. In this tutorial, we will be solving question 6 from a past Engineering Science N4 exam paper. This question covers the important topics of stress, strain, and Young's modulus. By the end of this video, you will be able to, first, define key concepts like bending stress. Second, solve problems involving shear and normal stress. Third, calculate strain and Young's modulus. And fourth, determine thermal stress. Let's begin with the first part of the question. Our first question, 6.1, asks us to define bending stress. Question 6.1. Define find bending stress. This is worth 2 marks. Before we look at the official definition, let's think about it logically. Imagine taking a ruler and pushing down on it from the top. What happens? The ruler bends. When it bends, the fibers on the top side are compressed, while the fibers on the bottom side are stretched or in tension. The internal force that resists this bending is what we call bending stress. So, how can we define it? The official definition is, bending stress is the stress that an object encounters when it is subjected to a load at a particular point, which causes an object to bend. Let's repeat that for clarity. It is the internal resistance, or stress, within an object when an external force makes it bend. Now, let's move to question 6.2, which involves a practical calculation. The question asks, determine the stress induced in the rivet shown in figure 3 below due to the shearing force of 55 kN. The diameter of the rivet is 35 millimeters. First, let's analyze figure 3. It shows a single rivet lap joint. The forces on the plates are in opposite directions. This means the rivet is trying to be cut, or sheared, into 2 pieces. This type of force that acts parallel to the surface of an object, trying to cause it to slide or cut, is called a shear force. Therefore, the stress induced in the rivet is called shear stress. The symbol for shear stress is tau, T. The formula for it is force F divided by area A. Let's repeat that. Shear stress tau equals force divided by area. Let's list the given data. The shearing force, F, is 55 kilonewtons, or 55,000 newtons. The diameter of the rivet, D, is 35 millimeters, or 0.035 meters. The first step is to calculate the area over which the shearing takes place. This is the cross-sectional area of the rivet. For a circular cross-section, the area, A, is pi times diameter squared, all divided by 4. Plugging in our values, the area is p times 0.035 squared, divided by 4, which equals approximately 9.621 times 10 to the power of negative 4 square meters. Now we have the force and the area, so we can calculate the shear stress. Using our formula T equals F over A, we substitute 55,000 newtons for F and our calculated area for A. The result is approximately 57,166,197 pascals. The answer in the memo is 57.165,857 MPa. Let's compare this with our result. The memo's answer can be obtained by using the formula T equal 4F/PD2 directly. This is because A equals PD2/4, so when you substitute it, the 4 comes to the numerator. Let's try that to match the memo. Tau equals 4 times 55,000 newtons, divided by pi times 0.035 meters squared. This gives us the same value, which we can round to 57.166 megapascals. Both methods are correct and yield the same answer. We now arrive at question 6.3, a multi-part problem that brings together stress, strain, and Young's modulus. The question is, a rod with a diameter of 25 millimeters and a length of 500 mm subjected to an axial load of 50 kN, which causes an elongation of 0.25 millimeters. We need to determine the stress in the rod, the strain, and the Young's modulus of elasticity. Let's start by listing our given information and converting it to standard SI units, which are meters, kilograms, and newtons. Given diameter D is 25 millimeters, or 0.025 meters. Original length L0 is 500 millimeters, or 0.5 meters. The axial load F is 50 kilonewtons, or 50,000 newtons. And the elongation or change in length, delta L, is 0.25 millimeters, or 0.025 meters. Let's tackle the first part of this question, 6.3.1. Question 6.31 asks for the stress in the rod. Since the load is axial, it's pulling on the rod's axis, so the stress we need to calculate is tensile stress. This is a form of normal stress. The formula for tensile stress, represented by the Greek letter sigma, is also force F divided by the cross-sectional area A. You can see how this is similar to the shear stress formula, but now the force is perpendicular or normal to the area. First, we need to calculate the area of the rod's cross-section. Using the same area formula as before, pi d squared over 4, we get an area of approximately 4.909 times 10 to the negative 4 square meters. Now we can find the stress. Stress sigma equals force 50,000 newtons divided by our calculated area. This gives us approximately 101,859,850 pascals. The memo's answer is 101.853 MPa. Let's see if we can match it. The memo used the value 4.909 kg/10^4, which is a rounded value. If we use that rounded area, we get 101,853,738 pascals, which is indeed 101.854 megapascals when rounded to 3 decimal places. This matches the memo's value. Let's continue to the next part of question 6.3. Question 6.3.2 asks us to determine the strain. What is strain? Strain is a measure of deformation. It's how much an object changes in size or shape compared to its original size or shape. The formula for strain, epsilon, is the change in length, delta L, divided by the original length, L naught. Let's use the data we have. The elongation, delta L, is 0.25 millimeters, which is 0.025 meters. The original length, L naught, is 500 millimeters, or 0.5 meters. Now we can calculate the strain. Strain epsilon equals 0.0025 meters divided by 0.5 meters. The result is 0.005. Notice that strain is a dimensionless quantity because it is a ratio of 2 lengths. This matches the memo's answer exactly. Now for the third part of question 6.3. Question 6.3.3 asks for the Young's modulus of elasticity. Young's modulus, represented by E, is a measure of the stiffness of a material. It tells us how much stress is needed to produce a certain amount of strain. Think of it as a material's resistance to being stretched or compressed. The relationship between stress, strain, and Young's modulus is given by Hooke's law. Young's modulus E equals stress sigma divided by strain epsilon. We have just calculated both stress and strain. Stress sigma is 101.854 megapascals, or 101,854,000 pascals. Strain epsilon is 0.005. Let's put those values into our formula. Young's modulus E equals 101,854,000 pascals divided by 0.005. This gives us approximately 203,708,000 pascals. The memo's answer is 204 GPa. Let's compare. A gigapascal, or GPa, is 10 to the power of 9 pascals. So our answer of 203.708 GPa rounds up to 204 GPa. The slight difference is due to the memo rounding the stress value first. This confirms our calculation is correct and consistent with the provided answer. We've reached our final question, 6.4, which deals with thermal stress. The question states, a 20 mm diameter steel rod is 1 meter long and is clamped at both ends. If the temperature of the rod is decreased by 55 degrees Celsius, calculate the stress in the bar. Young's modulus for the steel is 200 GPe, and alpha for the steel is 12 times 10 to the power of -6 per degree Celsius. First, let's understand the concept of thermal stress. We know that materials expand when heated and contract when cooled. In this case, the temperature is decreasing, so the steel rod wants to contract. However, the rod is clamped at both ends, which means it is prevented from contracting. This restriction creates an internal stress within the rod, the thermal stress. Let's list the given data, making sure to convert units where necessary. Now, let's derive the formula for thermal stress. If the rod was free to contract, it would change in length by an amount d delta. The formula for this change in length due to temperature is the original length L times the coefficient of thermal expansion alpha times the change in temperature delta T. But the rod is clamped, so it can't contract by this amount. The clamps are exerting a force that effectively stretches the rod back by the same amount dal to its original length. This change in length dal caused by the clamps induces a strain. Remember the strain formula? Epsilon equals dial over L. We also know the relationship between stress, strain, and Young's modulus. Stress equals E times strain. Now we can substitute our strain formula into the stress formula. Stress sigma equals E times dl over L. And since our change in length, dal, is equal to L times A times dot, we can substitute this entire expression for dal into the stress equation. This gives us our final formula for thermal stress. Stress equals Young's modulus E times the coefficient A times the change in temperature dt. This is the formula we will use. Let's apply our formula for thermal stress to solve the problem. The formula we derived is stress sigma equals E alpha delta T. We have all the necessary values. It is 200 times 10 to the 9th pascals. Alpha is 12 times 10 to the negative 6 per degree Celsius, and delta T is 55 degrees Celsius. The negative sign for delta T is very important. It tells us we are dealing with a temperature decrease. Let's substitute these values into the formula. Stress sigma equals 200 times 10 to the 9th, multiplied by 12 times 10 to the negative 6, multiplied by 55. Calculating this gives us stress sigma equals 132,000 pascals. Notice the negative sign. A negative stress value in this context signifies a compressive stress. When the rod tries to shrink but is prevented by the clamps push on the rod, compressing it. This is a compressive stress. The memo's answer is 132 MPa, without the negative sign. This often happens because the question asks for the magnitude of the stress. Our answer of 132 MPa correctly indicates a compressive stress of magnitude 132 MPa. Therefore, we can state that the stress in the bar is 132 megapascals in compression. This concludes question 6.4. Let's quickly review the steps taken in the provided marking guideline, which uses a slightly different order of calculation but arrives at the same correct answer. The guideline first calculates the change in length if the rod were free to contract, using the formula delta L equals L naught alpha delta T. Plugging in the values 1 meter for L naught, 12 times 10 to the negative 6 for alpha, and 55 for delta T, without the negative sign, just the magnitude of the change, it calculates a change in length of 0.0066 meters. Next, it calculates the strain induced by preventing this contraction. Strain epsilon equals delta L over L. Using the calculated delta L and the original length of 1 meter, the strain is 0.00066. Finally, it uses Hooke's law to find the stress. Stress sigma equals E times epsilon. Substituting 200 times 10 to the 9th pascals for E and 0.0066 for epsilon, the stress is calculated as 132,000 pascals. This gives a result of 132 megapascals, which, as we discussed, represents a compressive stress of that magnitude. As you can see, both methods are equally valid and lead to the same answer. It's important to understand the underlying physics that connects the formulas. Let's quickly recap what we've accomplished in this tutorial. First, we defined bending stress as the stress encountered when an object bends. Second, we calculated the shear stress in a rivet using the force over area formula. Third, we determined the tensile stress, strain, and Young's modulus of a rod. And fourth, we derived the formula for thermal stress and applied it to a clamped bar. You now have a solid foundation for solving problems involving stress, strain, and Young's modulus. Thank you for watching this tutorial from Math Zone African Motives. Subscribe for more tutorials from Math Zone African Motives.